Okay guys, let's continue here in 9.1 and use properties of cube roots now. Okay. In this case, we want to look for any perfect cubes we can pull outside of the radical, escape from the radical, if you will. Okay. And when I say use my factor tree and I say, oh, that could be negative 64 and 2, well, negative 64 is my perfect cube. So I can essentially apply that cube root to each of those individually. So the cube root of negative 64 times the cube root of 2. Well, what is the cube root of negative 64? In other words, what number multiplied by itself 3 times gets to negative 64? Well, that's negative 4. So negative 4 escapes from that radical, and that's gone. And what's left is the cube root of 2. So it'd be negative 4 times the cube root of 2 would be our answer. Okay, how about something like 125 x to the 7th? Well, if I have, say, a variable, well, I see 125 is already a perfect cube. I can always break it up into 125 multiplied by x cubed times x cubed times x. And I like to do it this way because then I know for each x I'm bringing out, I can account for it. Okay, so that's essentially the same as the cube root of 125 multiplied by the cube root of x cubed multiplied by the cube root of x cubed multiplied by the cube root of x. Okay, the cube root of 125 is 5. The cube root of x cubed is x. The cube root of x cubed again is x. And then I've still got 1, the cube root of x left. So that's essentially 5x squared times the cubed root of x. Okay, so anything we can pull out of the radical, notice the cube root of x cubed is x. The cube root of x cubed is also x, so that's why I have x, and x times x is x squared. And then I've got 1x by itself left under the radical that can't escape, okay? Okay, let's look at some more. The cube root of y over 216. Well, we can always apply that cube root to each individually by multiplication or division, right? Our quotient rule or our product rule applies here to cube roots as well. So the cube root of y is just the cube root of y, nothing we can do with that one. The cube root of 216 is, well, what number multiplied by itself 3 times is 16? That would be 6. So 6 escapes, and that would be the cube root of y over 6, and that's our answer, okay? D. Okay, the cube root of 8x to the 4th over 27y cubed. And that radical encompasses all of them there, okay? All right, so we can apply that cube root to all of them individually. The cube root of 8 times the cube root of x to the 4th over the cube root of 27. Essentially now multiplied on the bottom by the cube root of y cubed. Okay, let's do some simplifying. Well, the cube root of 8, that's 2. And with this cube root of x to the 4th, I can really write it as the cube root of x cubed times x. X cubed times x is x to the 4th. I just wrote it like that, so that when we simplify it, we'll see what's going on, okay? Okay, and then the cube root of 27 is 3. And the cube root of y cubed is just y. Notice one of those y's escapes. Okay. Okay, so then there's a little more simplifying to do here. Remember, I can then do that the cube root of x cubed, and do then also the cube root of x here over 3y. And what's the cube root of x cubed? Well, that's just x, so let's bring that out. I've still got the 2. Now I've got the cube root of x cubed is x. And then I still have the cube root of 1x upstairs, and I still have my 3y downstairs. So 2x times the cube root of x over 3y. Notice, anytime we've got a power here larger than our index, we need to separate it into multiples of our index and then whatever's left over if there's 1 left over, right? So I did 3 and 1, right? To get us to that x to the 4th here. Okay, so as we do these, remember we can apply the radical to the product of any two quantities or the quotient of any two quantities, and then we want to pull out all the terms that we can. That's part of the simplification. So we want to pull out everything out of the radical that we can, and if there's stuff left under it, then that's how it is, okay? And it has to stay underneath the radical. Okay, guys, let's now do this idea of rationalizing the denominator. Well, in order for a denominator to be rational, then we can't have a radical left in the denominator. And so we have to, in other words, get rid of this radical here. Well, if we've, say, got a square root here, then we're going to multiply by whatever's underneath the radical, top and bottom. Here, in this case, 3n. Notice, if I do that top and bottom, I've essentially just multiplied by 1 because those two things over each other cancel to 1. So I'm just going to change the form of it. I'm not going to change the value of it. Okay, now when we multiply these radicals, what's underneath by what's underneath? So the radicand by the radicand. Root of 5 times the root of 3n would be the root of 15n. And then root of 3n times the root of 3n, cross numerators, remember, and across denominators, would be the root of 9n squared. Well, that's the same as the root of 15n over the root of 9 times the root of n squared, what we just practiced. Okay, so that'd be the root of 15n over the square root of 9 is 3, and the square root of n squared is n. So notice now I don't have anything left underneath the radical in the denominator, okay? And it's only in the denominator that we're worried about. And could I say cancel this 15 to the 3? No. Or the n to the n? No, because one's underneath a radical and one's outside of a radical. Only things that are outside we can cancel, or things that are both underneath we could cancel. Okay, so this would be our answer. Okay, let's do another one. Two over the cube root of n. Sorry, over the cube root of 9. Now, cube roots are a little more interesting because we don't just multiply by the exact same thing top and bottom as we did for the square root that's, say, underneath the radical like it was there with that 3n here, okay? Here we have to say, what are we going to multiply by the cube root of top and bottom that will get me to a perfect cube? Well, I have 9 here. Well, if I multiply by the cube root of 3, and then if I do it down here, I have to do it the same thing in the numerator, then I'm left with 2 times the cube root of 3 upstairs. And then I'm left with the cube root, say, of 27 downstairs. Well, why did I pick 3? Well, when I multiplied 9 and 3 and got 27, 27's a perfect cube here. So the cube root of 27 is 3, right? So I'm left with 2 times the cube root of 3 over 3. Okay, and now can I cancel the 3's? No, one's underneath and one's outside. Okay, so it's just going to be 2 times the cube root of 3 over 3. Okay, and that would be our answer. Okay, so notice with cube roots, we didn't multiply by the exact same thing underneath here. We multiplied by something that got us to a perfect cube root. In this case, it got us to the smallest cube root between 9 and 3, got us to 27, and then we could escape that 3. And notice we no longer have a radical in our denominator. Okay, so that's the idea of rationalizing the denominator. Okay, so this should be enough to get you started on a few of these to practice, and then we'll get into more depth as we go. Okay, thank you.